hopefully OBS is recording through my headset mic instead of the webcam mic. I guess we'll find out when I upload it later. Okay. So the lab this week is pretty simple, pretty straightforward. It is really just doing a couple conversions. One of which is, it's more complicated than I make it sound there, but one of them is a pretty simple conversion, and then the other one is a slightly more complicated conversion, but still not something we haven't done before, as everything we're going to do in this lab is something we've done before. We're going to have a new equation that we've never seen before, but all of the individual processes we've all done before. So we're going to take some data, do a little bit of math to it, and then graph it, and pull some information from the graph. And that's the whole lab. Again, all those things we've done before. We have done conversion processes lots of times. We have graphed data multiple times. We have pulled information out of a graph multiple times. So this is all stuff we've done before. We're just now going to do it with respect to KSP. So I guess we can just read it. It's not very long, so we can just go ahead and read it. So we have an overview here. It says magnesium hydroxide is sparingly soluble in water. So today we will study the thermodynamics of its solubility and determine the value of KSP at various temperatures. Further, if we know K at a few different temperatures, then we can determine the value of delta H and delta S for the reaction. So that is the solubility process that we're going to be looking at. The value of KSP at each temperature will be determined by measuring the pH and using that value to calculate the concentration of the hydroxide ions in the saturated solution. Now, for our purposes, we will not be actually measuring something, unfortunately. If we were in the lab, we could have something like this set up, have it very highly controlled in terms of its temperature, and measure the pH at those different temperatures. Since we're not in the lab, and you don't have access to magnesium hydroxide, at least I don't think you do, you probably shouldn't. It's not super dangerous, but it's not super safe either. We are just going to have the data given to us, essentially. So if you go to the Blackboard site, go to the labs, this is now available, oh sorry, not that one, this one. This is now available for you all to look at. So the handout thing, that's actually what we're just looking at there. So this is the handout. And then the simulation, if we click on that, is really not much of a simulation. So we open this up. We just have a spot to put our T number. I'm just going to make something up. There we go. Hit enter. And when we do that, go to the next page here, the next tab down here at the bottom, and there's our data. So, not much of a simulation. Just put in our number so that everyone gets slightly different values, and then it gives us some different temperatures and pHs to go along with that. So that is how we're going to get our data. So let's go back here to the simulation handout. Okay, so it says use the simulation file to determine which sample set of data to use. The sample data shows what pH was measured to be at different temperatures. You're then going to use Excel to make the necessary calculations to prepare your chart. So we are going to be graphing an equation that is called the Van Hoff, I think that's how it's pronounced, I don't think you pronounce the T. I don't think it's the Van't Hoff, but maybe it is. I've never actually heard someone speak that name. I've only ever read it. So I'm going to go with Van Hoff, because that's easier to say than Van't Hoff. Plus, I know that the hard T sounds don't always sound good on the microphone. So we're going to go with Van Hoff. So we have the Van Hoff equation here. This is a really cool equation that is used by combining these two equations. Now, we haven't actually gotten to these equations yet. These actually will show up in the chapter that we're getting to right now, chapter 16, the thermodynamics chapter. So if you're like, what the heck is delta G? Where did that come from? Don't worry about it. We will get to that in the chapter. For doing the lab, you don't actually have to know what delta G is, because if you notice here, it actually doesn't even show up in the Van Hoff equation. What does show up is the enthalpy, which you have seen before, the K value, which is actually the KSP value, because that's the equilibrium constant for the solubility. We just don't have SP showing here, but that is the same thing. So the K here is the same as the K up here. It's just we left the SP out, because this equation works with any kind of equilibrium, not just KSP. So we've seen this before. We've seen delta H before in Gen Chem 1. R is just the same old R that we always have. It's just the gas constant. T is the temperature in Kelvin. So we've seen that before as well. There's R again. Same R's over here. And then delta S we have not seen before, but we did actually just talk about it a minute ago, because that is actually the entropy. So that is the entropy values for our system. And I know here we're talking specifically about the entropy of the surroundings there in that slide. Don't worry about system versus surroundings at this point. We're just going to go with delta S. That's the change in our entropy. So other than delta S, everything else here we've seen before. And the delta S is the entropy value, which we're getting introduced to this week. So like I said, don't worry about delta G. You've never seen it before. You'll see it in next week's videos. That is what's called the Gibbs free energy. And that's essentially what we're used to equate these two, since in this equation delta G is equal to this stuff, and then in this equation delta G is equal to this stuff. We take those two equations and set them equal to each other, and the delta G's go away, and so we have this is equal to this. So that's where we got the Van Hoff equation. So we're going to be graphing this equation. To do that, we need to get the natural log of K, and we need to get 1 over T. Those are our two variables. Because everything in these two, the negative delta H over R, delta S over R, those are constants. So the delta H and R, the delta S and R, those are constants. So those are not part of our variables. It is just the K value and the T values that are changing. So we need to get the natural log of KSP, and we need to get 1 over the temperature. And this lab handout is so nice because it just explains to you how you're going to get those. It walks you through the process of getting both of those. So you don't even have to work out the overall map, so to speak, of how to get from one thing to another. It's just straight up given to you. So in the lab data, we are given the temperature in Celsius, and hopefully you are fairly comfortable converting the temperature in Celsius into Kelvin. That should be something you've done many times up to this point. I'm just going to add 273, or if you prefer 273.15. That converts it to Kelvin, and then you have one last thing to do, which is to divide 1 by that temperature. And so that will give you 1 over T. Don't forget that last step. That is a relatively common mistake. Students forget to do 1 over T. They just graph T. You will not get the right graph if you don't do 1 over the temperature. So the temperature is pretty straightforward, not too bad. The other one is a little more complicated because we need to go from the pH to the natural log of KSP. Now, this is most certainly doable, but it is most certainly more difficult than just converting Celsius to Kelvin. But the overall pathway for doing that is laid out here, and it's pretty straightforward when you see the overall process. So to get the natural log of KSP, obviously we need KSP. Taking the natural log is the easy part. Getting the KSP is the harder part. So if we need KSP, actually let me see if I can just do this over here. Will it let me write? Maybe not. It's not going to let me write on this. Okay. Well, let me just open something else up, I guess. So if we're trying to find KSP, in our case, because we have this reaction, so this reaction is happening here. So we have our magnesium hydroxide dissociating into magnesium and 2 hydroxides. Our KSP is this. So that should look pretty familiar to you, since we just did that last week. For the exam, we had KSP stuff where you should be doing things like that. So that should be pretty comfortable for you. So if we're trying to find KSP, we need this. That means we also need these. We need the concentration of magnesium, and we need the concentration of OH-. But we're not given either of those in the data. Instead, we're given the pH. But if you remember from chapter 14, I believe it was, if we have the pH, we can use that to get H+, because we know the pH is equal to the negative log of the H+ concentration. So if we have the pH, we can plug that in here and we can solve for H+. And if we have H+, if you remember from that same chapter, we can get OH-, because, if you remember, the concentration of OH- times the concentration of H+ is, in aqueous solution anyway, always equal to 1 times 10 to the negative 14. So, sorry, that one goes there. So this equation is for this arrow here. This equation is for that arrow. So if we can use this to find OH-, well now we have that part. That's part of our KSP. That's part of what we need. But it doesn't give us magnesium. However, if we think back to what's actually happening, if we think to the actual chemical process that's occurring, if we know how much OH- is in solution, the only source of OH- is our chemical reaction that's occurring. That's an assumption that we have to make, and we have no reason not to make it. There's no reason for us to believe that there's something else going on. So if this is our only source of OH minus, that means that this is also our only source of magnesium. And we know the ratio between the two, which then allows us to find the concentration of the magnesium. So essentially, whatever the concentration of OH minus is, one half of that concentration is equal to magnesium. Or if you prefer, well, it's the same thing here. Just take essentially whatever the concentration of OH minus is, divide it in half, and that's the concentration of the magnesium. Because again, it's a 2-to-1 ratio in our equation here. For every 1 magnesium that is made, we get 2 OHs. So whatever the concentration of OH is, just divide that by 2, and that's the concentration of magnesium. And so then at that point, we now have both of those concentrations, which allows us to get the KSP, and then we just take a nice little log to our is it log base 10? I think it is log base 10. Go back here. No, it's the natural log. So take the natural log then of the KSP, and that will give you your Y value here. And so it is a little bit of a trek to get from the pH all the way to the natural log of KSP. But each of those individual steps that we took there, we've done all those before. I just don't think we've done all of them together before. But we've used the pH to find H+, we've used H+ to find OH-, we've used the concentration of one thing in an equation to find the concentration of something else, and we've calculated K values. Like, we've done all of these things before. We're just putting them all in a row, one right after the other. Okay, so you will do that with all 6 of these, I think? Yes, all 6 of those. Now, if you want to do all 6 of those by hand, that's not the worst thing in the world to do. It's not terribly hard to do. There's only 6. And honestly, probably I would just do them by hand, because the time it would take me to write out the Excel equations would probably be just the same amount of time that it would take to just do them in my calculator. But if you would prefer to actually work it out in Excel, you can do that too. It's up to you. Either way is fine, but you should end up with a 1 over t and a natural log of the KSP column that you are going to plot. And so you will have 1 over t as your x, natural log of k as your y. Make sure you have those correct. That is another very common mistake, is students will get those flipped. And you will have the 1 over t as your y and the natural log of k as your x. You will not end up getting the correct answer if you do that. So make sure that you have those correct. And you'll just plot it exactly like we've done multiple times before. I'm not going to go through and make a plot here, because we've done that in like the last 2 or 3 labs. So I trust that you know how to do it at this point. And if you can't remember, then you can go back and watch the videos from those previous labs where I make graphs, just to get a refresher. But you're just going to make a graph of the natural log, or of 1 over t versus natural log of KSP. You're going to put a line to the graph, just like we've done in previous labs. You're going to take the equation for that line, and you are going to pull out of it the slope and the intercept. And so you're going to end up with the slope is equal to negative H over R, and the intercept is equal to delta S over R. I don't think there was a negative there. So you're going to actually insert the actual number for each of those here. So you will get a number from the graph for the slope, you will get a number for the intercept from the slope, and you will just plug those numbers in and solve for delta H and delta S. Don't forget that negative there, by the way. So if the slope of your graph is negative, then those two negatives would cancel out and you'd end up with a positive delta H. Okay. And again, that's something we've done before too. When we did the Arrhenius equation stuff, you're pulling things out of the graph and solving for a part of the equation. So this is all stuff we've done before. Okay, so what you're going to turn in is a document showing the chart with the trend line. So I need to see the data, I need to see the equation, and have the please label the x and y as well when you're doing that. You need to see your values for delta H and delta S, so there should just be one number for each of those. You're not going to have a different number for each data point. You remember, you're just pulling it from the graph itself, from the equation of the line. So you'll have one number for delta H, one number for delta S, with the correct sign and units. And then and it actually just tells you the units there, so it's not a big secret. And then show your work for these questions here. So there's a few questions that I would like you to answer. And some of those will be, especially the ones where it talks about delta S, you will need to watch the videos for this week before you can really make sense of those, because it is talking about entropy and, you know, having positive entropy versus negative entropy. And that won't really make sense until you watch the videos this week for entropy. So make sure you watch those, and you should be good to go. Let's see here, hold on. We do have one little thing here at the end. So use the values of delta H and delta S to calculate the value of delta G and K at 5 degrees C. So to do that, you're going to have to use these equations that it gave you here at the beginning. Now, you don't have to understand these equations to be able to solve those for what it's asking for. So for example, here it says find the value for delta G at 5 degrees C. You don't actually have to understand what delta G is to solve this equation and get that, because you'll have delta H, you'll have delta S, and it tells you that you're at 5 degrees C. And so you can just convert that to Kelvin. This does need to be in Kelvin. Everything here needs to be in Kelvin. So you're going to convert that to Kelvin, and you can just plug the numbers in and you'll find delta G. So you don't even really need to know what delta G is to solve that. And it's then kind of the same thing here. Take that delta G value, plug it in here. You already know R. T's the temperature in Kelvin at 5 degrees C, and you can solve for K. So you don't actually need to know what delta G is to solve that. I would encourage you, though, to go ahead and watch, I think it's just one extra video past what's assigned for this week. So this week it goes up to video 7, I believe. And if I remember correctly, video 8 is actually where I introduce delta G and Gibbs free energy. So you don't have to know what delta G is to solve this and answer the question, but I would encourage you to go ahead and watch that one extra video so you can see what delta G is. So even though you don't actually need to know what it is to be able to answer the question, you know, it gives some context and some makes it more meaningful, I think, as you're solving those. And so then you would just do the same thing for 95 degrees. So it's just a higher temperature. Okay. So there's a bit of math here in this lab, but overall there's not a lot going on. It's not super complicated with multiple graphs and taking data from one graph and plugging it into another or anything like that. I think it's fairly straightforward. But if you have any questions, I'd be happy to answer them now. Although I bet most of the questions will come up as you actually get into it and start doing it later this week. So feel free to email me about those if you would like. Are there any questions right now about that? Good. Like I mentioned, it's like everything we're doing there is very similar to what we've done before. It's just kind of doing it with a new equation, which is not necessarily a non-trivial thing. It can be confusing to do something with a new equation, but hopefully everybody will be able to work that out without too much trouble. Okay, well, if there aren't any questions, I think I'll go ahead and let you all head out for the day. So, like I mentioned, make sure you watch the videos, make sure you're working on the lab. I did move the due date for the lab out just a couple days because I didn't realize that for some reason last semester I had the availability date for the lab set, and so it wasn't visible until today. I thought that you all could see it before today, but since it wasn't visible till today, I pushed the due date to Wednesday, I think. So you have a couple extra days, but I don't plan on doing that for the rest of the lab. So make sure you get that work done, and I will see you all Thursday.